So without further ado, the moment you've all been waiting for, the stupendous, most exciting, excellent lesson ever for AP Stats is about to start. I know you can hardly wait. Let me give my 75 clicks so that I can present properly. Why did I do that? That's not the right click. Dang it. Oh well. That's what I want. Oh man. See, I clicked the wrong thing and then everything goes haywire. That's better. All right. So here we go. It is Tuesday, October 20th, 2020, the year that never ends. We are going to be completing section 2.1 about describing location in a distribution, dealing with percentile and z-score. We're continuing where we left off last week. All right. So a quick review of percentile. A percentile tells you the percent of observations less than the observation being considered. This is important. It is telling us what percentage of things are less than that value. Okay. For example, if you scored a 75 on a test and you are at the 95th percentile, then you scored better than 95% of the students who took the test. 95% of the people who took that test did worse than that. They had a lower score. This also means that 5% of the students who took the test scored the same or higher as you. Okay, so those are the two ways that we can deal with the 95th percentile. 95% had a lower score, 5% had the same score or higher. Okay, this is a quick review of what percentile means. Can you raise your hand if you need a moment to write any of this down? All right, we shall pause. Excellent. So now we have our standardized score or z-score. Again, this is a review from our previous class. The standardized score describes how many standard deviations a value is from the mean. That's what our standardized score will tell us. A z-score is positive if the value is greater than the mean, or to the right of the mean in the distribution. A z-score is negative if the value is less than the mean, or to the left of the mean in the distribution. So we can have positive or negative z-scores. You can standardize a score with this formula. We use z equals x minus x bar divided by s sub x, which this all has a meaning, right? The x, okay, this represents the observation. X bar is the mean of the sample. And S sub x is the standard deviation of the sample. right? And Z is just the letter we use to represent our standardized score. Now, it is important to note that we have to say sample in this. That's what this notation refers to. The X bar is the mean of the sample. The S sub X is the standard deviation of the sample. Unless we've been told that we're dealing with the values from an entire population, or we're provided the symbols that imply the entire population, we're assuming we're dealing with a sample. Okay, this rule would change slightly if we're dealing with a population, and it would change, that's what color I want, right? Z and X would stay the same. Z equals X, it would be minus mu, which is the mean of the population, divided by sigma of X, where sigma is the standard deviation of the population. Right? These two notations imply the population is, we have the numbers for the entire population. Okay. Right, the mean of the population. And this is the standard deviation of the population. Okay. Other than that, the formula is exactly the same. We do the same operations. It's just the notation changes to show that we're dealing with either the sample or the population. Okay. Would you raise your hand if you are writing stuff down from this slide and you need more time? All right. Looks like we're good to go. All right. So we can compare data using z-scores. All right. So here's an example. We have a student who scored an 86 on a first test and an 82 on a second test. Just based on this, we would assume that the student did better on the first test, because 86 is bigger than 82. Right? The mean of the first test was 80, the standard deviation of 6.07. Right? And we have the mean of the second test was 76 with a standard deviation of 4. Right, so the question we want to answer with this is, which test did the student perform better on relative to the class? So based on how the entire class performed, which test did this student actually do better on? So to do that, we calculate the z-score, right? Whichever test results in the better z-score is the test that the student performed better on relative to the class. So we can do this calculation. All right, so we have our first test. We'll do the z-score here. We have z equals 86 minus 80 divided by 6.07. And when we put this into the calculator, we'll get 0.988, blah, 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 blah. We'll round that to 0.99. And on the second test, our student has a z-score that is equal to 82 minus 76 divided by 4. And that results in a z-score of 1.5. So compared to the rest of the class, relative to the rest of the class, even though the student's score itself was lower than the first test on the second test, the student performed better relative to the rest of the class on the second test. And this is demonstrated because she's 1.5 standard deviations greater than the average on the second test. And on the first test, she's only one approximately standard deviation better than the average on the first test. Right? So the student performed better on the second test. Are there any questions on this type of calculation and how we can use the z-score in comparing these types of things? Okay. All right. Does anyone need another moment to write anything down? Okay. Moving on. So the next topic is transforming data. What we just did with standardizing scores, that's one way to transform data. We're taking something in one unit, in our example it was test scores, and converting it to the standardized score, which tells us how far away it is from the mean. Right? And that's a transformation of the original data to another unit, another way of measuring it. And transforming data allows you to change the units of measure to make comparisons easier. Just like we saw in our example with the test scores, the two tests are different things. They're probably covering different topics, and the range of scores and average of scores were different. So it's not always fair to compare just the two test scores as raw data. Right? We want to compare them based on how well everyone in the class did on those tests. Right? So it's almost like we're able to compare how well you did based on the difficulty of the test in this case. So it allows us to say, even though the student had a lower score on the second test, the student performed better relative to the rest of the class on the second test. Right? So again, an example of things we can compare by transforming the data are ACT and SAT scores. ACT and SAT scores are measured on entirely different scales. The ACT, I believe, is like out of 35 points or something like that, and the SAT is out of 1600. Right? So I can't just compare raw scores. They don't compare that way. Right? They're too different. But if I transform those scores into the same type of unit, right, a standardized score, and convert all the scores to how far away they are from the mean, I can compare those values to say, okay, well, who did better, right? Or if a student did better on the ACT or the SAT based on their standardized score. And so it allows us to do comparisons of things that were originally in different units. Right? You can use this to compare distances, kilometers and miles, and averages, things like that. Comparing grades from percentages and 4-point scales, right? Percentage grade and a 4-point scale can be greatly different in how they're measured. But if we again look at our mean and standard deviation and standardize these things, we can compare things that were originally in different units. All right. So we're going to look at an example of what transforming does to our data. What values within our shape, center, and spread does transforming data change, as we're going to look at next. Can you raise your hand if you need another moment to write anything down from this slide? So first we're going to look at this set of data here. We have students were asked to guess the width of their classroom to the nearest meter. Their guesses are displayed on the dot plot below. Right, they were asked to guess in meters because they aren't as familiar with meters, right? So they're more familiar with measuring in feet, like you or I might be, because in the United States we use feet rather than meters for most things. And so the guesses were kind of wildly different. So we get this dot plot, which has our room width guess in meters. Right, so this is our original raw data. We have some of our statistics down here. Okay. We then converted the data from the raw data, which is on the bottom here now, to the error in room width guess in meters. To calculate the error, we just subtracted the actual room width, which was 13 meters, from the guess that each student made. So if you actually guessed 13, you would have an error of 0. Right? So we had 3 students who had no error. They guessed right at 13. If you were too low in your guess, you wound up with a negative number on this. If you were too high, you wound up in a positive number. So now, when we subtracted a number, and we're looking at specifically the effect of adding or subtracting a constant is just another word for a basic number, right? What stayed the same? Of our shape, center, and spread type of things, what stayed the same when I subtracted a number? What summary statistics remained the same? Now I'm actually asking you guys if you can type in the chat or unmute your mic. What stayed the same? Or you could answer what changed. Think about our summary statistics, the shape, right? Measures of center, the spread, location, right? Percentiles, quartiles. What stayed the same and what changed? Yes, these are the shape stayed the same. Right? We can kind of observe that, like the shape looks exactly the same. Right? So our shape stayed the same. That's one. What else, guys? What else stayed the same or changed? We can think about our measures of center, like mean, median, the quartiles, right? Our measures of spread, percentiles, things like that. The range, the actual measurement of the range or the IQR, did those change? All right, so we also get like the measure of the range, if the actual value of range stays the same. The value of the IQR will stay the same as well. right? If we think about it, the range is from -5 to, I think, 28 or 27, -5 to 27 on this. So the value of the range, 27 minus -5, is 32. And on the other set of data, we go from 8 to 40. 40 minus 8 is also 32. So the value, right, when we find the value of the range, stays the same, 32 for both. The same is going to happen with the IQR. The interquartile range will also remain the same. Right? But our measures of center and our locations will all change. They're all going to shift. Right? So we think of center, that's going to change, right? Thinking mean and median. And we can see that on the graph, right? The mean and median have to move. They can't be the same value anymore. Right? The center and location, right? Think of like percentiles, quartiles, right? Location numbers change. So in a nutshell, the effect of adding or subtracting a constant, right? Adding the same positive number, A, to each observation, adds A to measures of center and location, right? Mean, median, quartiles, percentiles, but does not change the shape of the distribution or measures of spread, range, IQR, standard deviation. Right? Those will remain the same. So adding or subtracting will not change the value of the range, IQR, standard deviation, or shape. It will change measures of center and location of values. Right? The location of the median and the quartiles will change. What questions do you have? Can you raise your hand if you need a moment to write this little tidbit of information down? Right. We shall pause. All right, next. We're going to look at transforming data, but the effect of multiplying or dividing by a constant. So we just looked at what adding or subtracting does. Now what happens when we multiply or divide. So we're looking at the same set of data, but we're now converting the error data to feet. That unit of measure is more familiar to the students. Here's the new data compared to the original error data. So on top here, we have our original error data, which goes from -5 to 27 in meters. And we have our converted error data that is now using feet, and that goes from, that's about, I think, -8 to about 89. All right. So now, what is something, well, what's the only thing that stayed the same? There's only one thing that stayed the same when we did this type of transformation. What stayed the same? There's only one thing. Yes, these are correct again. The shape, right? We can easily see within these dot plots that our shape stayed the same. Right? This kind of means that no matter what type of transformation I do to my data, shape's going to stay the same. I can add, subtract, multiply, divide. Shape will stay the same as my original data set. That's nice. However, when we multiply or divide, we will have changes to everything else, right? The range, right, is going to be bigger, right? We multiplied by a number greater than 1, so we're going to have a bigger range in this case. We could divide and get a smaller range, right? Where the center is, right, mean and median, that's going to adjust, right? All of the other parts are going to be adjusted by a certain amount, depending on what we're multiplying by. Right? But when we multiply or divide, the only thing that stays the same is the shape. So again, we have this little tidbit of information here. When you multiply or divide each observation by the same positive number b, right, you multiplies the measure of center or divides and location, meaning the mean, median, quartiles, percentiles, they will be multiplied by that number or divided by that number. It also multiplies the measures of spread, your range, IQR, standard deviation. So essentially everything gets multiplied. The only thing that doesn't change is the thing that is not a number, which is the shape. That will remain the same. So we want to be aware of these rules because it allows us to predict what a distribution will look like when it's transformed. And it allows us to make adjustments to measures of center or measures of spread without having to get all of the new data points again. Okay. Can you raise your hand if you need a moment to write this down? Looks like we're okay. So let's look at some examples of transformations within problems. All right, so we have two little example problems here. All right, we have Sam. When he goes to a restaurant, he always tips the server $2 plus 10% of the cost of the meal. If Sam's distribution of meal costs has a mean of $9 and a standard deviation of $3, what are the mean and standard deviation of the distribution of his tips? All right. So we have an addition and a multiplication going on here. We're adding $2 and we're also multiplying by 10% to figure out what the tips would be, right? We're going to take whatever the cost is, multiply by 10, then add $2 to find the value of the tips. So if we have a mean of $9, we know that the mean is affected by addition and multiplication. So it's going to get both operations. Okay. So to find the new mean, we take the $9 and we multiply it by the 10%, 0.10, and then add the $2. Right, so we found what's 10% of 9, and then add the money. We get $2.90. This is the mean of the tips. The standard deviation is not affected by addition. That will not change the value of the standard deviation. However, the multiplying by 10% will. Okay? So the only operation we need to do for the standard deviation is the multiplying by 10%. So we just take the $3, multiply by 0.10. That will give us 30 cents. And this is the standard deviation of the tips. Right, so they don't both just automatically get the same calculation. They only get the part of the calculation that has an effect. Right, so the mean, because it's affected by addition and multiplication, gets both. Standard deviation, because it's only affected by multiplication, doesn't need to worry about the addition. Right, so we only do the multiplication. Any questions on this first example? All right. So in example number 2, we're looking at ACT scores. So scores on the ACT college entrance exam follow a bell-shaped distribution with a mean 18 and a standard deviation 6. So a mean of 18, standard deviation of 6. Wayne's standardized score on the ACT was negative 0.5. What was Wayne's actual ACT score? In this case, we're using what we know about how to calculate a z-score to reverse the transformation back to our original score. Right? So we just fill in what we know. We have the z-score of negative 0.5, and that needs to be equal to the original score minus the mean, 18, divided by the standard deviation of 6. So we have to multiply each side by 6. Right, that cancels out the division by 6. That results in negative 3 equaling x minus 18. Add 18 to each side. We get 15 equals x. That means the original score, right, Wayne's score, was 15. Right, and we just undid the transformation.